Okay, cool.
Yes.
So here's the contents of what I'm gonna speak about today. So first, just an introduction to what makes HyperEVM unique, like why is it different to all the other EVM chains that we have? And then some nuances for developers who want to leverage this uniqueness of HyperEVM. And then also a few security considerations that are important for any developer if you're using these unique aspects of HyperEVM. And then finally, I'll go over the HyperEVM lib, what it is, why developers will find it useful, and how it can save you a lot of time when building smart contracts for HyperEVM. Okay, so first, just what makes HyperEVM unique. So with Hyperliquid, we have HyperCore, which is a blockchain which consists of the highly performant spot and perp order books, which are the initial iteration of what Hyperliquid is. And then we have the EVM side, which lets any builder build any EVM smart contracts. But the cool part is that the HyperEVM can interact with HyperCore, and it can read information from HyperCore, and it can also perform trades and do any actions like staking Hype or depositing into vaults on HyperCore. And that's really the unique aspect of HyperEVM compared to other standard EVM chains. So the overarching idea is, like, imagine if contracts on Binance Smart Chain could somehow be plugged into Binance's order books and read data from them, interact with them, and be and give builders the opportunity to build decentralized apps that can work with the deep liquidity that Binance has on their centralized exchange. But obviously that's not possible on BNB. But with Hyperliquid, we have HyperCore, which is a highly liquid, highly performant spot and perp order book, and now the EVM can interact with it. And the two main components that developers will be working with, one of them is called the CoreWriter, which allows your smart contracts to perform actions on HyperCore, and it's a system contract deployed on HyperEVM. And the other aspect, which is for reading data from HyperCore, are called the read precompiles. So so there's many different read precompiles for each different piece of data that you might want to read. So I'll just exit the PowerPoint for a second. Just checking if you're still able to see my screen.
Yeah, we can see your screen.
Yes?
We can see your screen. Yes.
Okay.
Yes.
So let me just go to, so this is a contract called L1 read, which is, it just demonstrates all the different precompiles and the information that you can read from HyperCore. So one example is the account margin summary. So you can pass in a user and the perpdex index, which we can talk about what that is later. And then it would, okay, I don't have an example user right now, but let's just move on. So we have the prices, the mark price of a perp asset, and then the oracle price. And then we have the perp asset info. And if we want to see what this contains, we can just check the contract. So yeah, so for perp asset info, we can obtain all of these details of a perp asset. And then in terms of hype staking, we can, so we have the delegator summary struct, which is returned by the delegator summary precompile, and so on. So we just have all of these different precompiles at these designated addresses, which allow us to read information from HyperCore. Okay, so let's see some like examples of apps that are uniquely enabled by these features of HyperEVM. So one is just that now you can tokenize any perp positions which exist on HyperCore, and you can bring them onto the EVM as an NFT. And once you've done that, you can, one example use case of this is you can borrow off of that NFT using it as collateral. And so let's say you had a long position on Bitcoin with the max leverage, which is a 20x, but you wanted even more leverage, or you're that bullish. So you can use that perp position as collateral to borrow USD on the EVM if there was a protocol that allowed this. And then you could use that USD to add to your long position, effectively having even more leverage on Bitcoin. And an example of a project working on this right now is Sentiment, so you can check them out. And then another unique like app that is now enabled by HyperEVM's unique features, the CoreWriter and read precompiles, is you can have a fully on-chain delta neutral stablecoin. So currently, stablecoins like Athena, which use a delta neutral carry trade to generate yield on the back end, a lot of their position is in centralized exchanges like Bybit. So there's a central point of failure there. But now, since we could use since HyperCore can be used as the location to short. Oh yeah, I should probably just describe how these stablecoins work first. So the way they work is having a delta neutral position on some token. So with Athena, it's a delta neutral position on ETH, where they hold ETH and also short it. And when they short it, they earn funding fees from the perp position. And this is how they generate yield for USDE. But the issue there is that the perp position is on a centralized exchange. So now with HyperCore, you can have with HyperCore and the EVM, you can have a stablecoin minted on the EVM, but on the back end, the carry trade works by moving the assets which are deposited on the EVM into HyperCore, and then performing the short, the perp short on HyperCore. And then because of this, there's no like central user who's like performing these trades. It's all governed by the smart contract, which is interacting with HyperCore through the CoreWriter mechanism. So essentially, this enables Athena-styled stablecoins to be fully on-chain, which is a unlock only due to HyperEVM's ability to plug into HyperCore. And an example of a protocol working on this is Delpho. And yeah, so the point here is there's many different unique DeFi applications which are possible due to the CoreWriter and read precompiles, and HyperEVM being able to connect to HyperCore.
Wow. Juan, I have a question here. So how does this interaction works? Like it's just an API call that I have to do to get the details out of HyperCore. Let's say I'm long on Bitcoin, like 20x long. So if I need that information onto my app on HyperEVM, I just need to do a API call.
Yeah, good question. So I'll go back to the L1 read.
Yeah.
So this shows us all the precompile calls we can make. So if we wanted to find the information of our perp position,
Yeah.
we would use this position precompile here.
Hmm.
And then so we could pass in the address of the contract and then the perp, which is essentially an identifier. So for Bitcoin, the identifier is 0. I can go over later how to find these identifiers.
Yeah.
So essentially we'd pass in 0 here as the perp asset ID, and then the contract address. And then if we go to the position struct here, so it shows us the leverage. It shows us the size, which is just how much Bitcoin we're either long or short. So it's an int 64. So let's say we were long one one BTC as the total amount of Bitcoin we're long, then this would be one and then a certain amount of zeros depending on the decimals. And then entry notional, which is the notional value upon entry of the position. And then this is it's a value only relevant if your perp position is isolated, which is not by default. And then so this just tells you if it is isolated or not. So so this is what you'd use to query the information. And the way it works is you could essentially even just call the L1 read contract via your contract, and you could just call this exact contract here, call the position function, the view function, and then it calls the precompile like this, and then returns you your position struct, which the precompile returns. Does that make sense for how you query the information?
Yes, understood. That makes sense. Yeah. Interesting.
Okay. Yep. So we'll move into some nuances for developers when working with the CoreWriter and the precompiles. So the first one is just that on HyperCore and HyperEVM, the decimals, like the amount of decimals used when representing integer token amounts, is different. So, for example, with Hype, it's represented with 18 decimals, just like ETH on ETH mainnet. So one Hype would be 1 times 10 to the 18. But on HyperCore, the decimals are 8. So to represent one Hype, it would be 1 E8. So this means if we bridged one Hype from the EVM into HyperCore, then suddenly the balance, like when we query their balance on the EVM, it says 1E18. But then after bridging, when we query their balance on HyperCore, it says 1E8. So you can see how it's pretty easy to mess things up. Like, what if you were trying to send on HyperCore, if you were trying to send your Hype to someone else, let's say, then if you typed, or your contract inputted the EVM amount, which is 1E18, then it would be way too much for HyperCore, and then it would just not work. So it's key to always keep in mind which decimals the amount is represented in whenever you're working with token balances or token amounts, to make sure that they're always correct. So I'll demonstrate how the token info precompile can be used to figure out how many decimals each token is represented with. So we'll go back to L1 read. Okay, so there's a token info precompile. And let's just find the address of some token. Yeah, so let's pick USDTO. So we can see that on the EVM it has 6 decimals. So here, another weird aspect of HyperEVM is we need to pass in a uint32, the token ID, rather than the token address. So in order to get the token ID, there's actually no on-chain there's no native on-chain mapping to do it, which is why we built this token registry, where we can go to this contract and then we can pass in any EVM contract, and then it tells you the token ID. And this ID is basically the representation of that token, but for HyperCore. So on the EVM, they have these addresses that we're used to. And then on HyperCore, they just have these uint32 numbers. So now that we have that number, we can go back to L1 read and then put that in. Okay, so now we have all this info returned by a precompile. So that's indeed USDTO, that's the name. And let's see. So if we go back, so there's all this different information, but if we go back to the code, these are the things that we're interested in. So it's actually just these two. So way decimals just represents the number of decimals used to represent the token amount on HyperCore. So for the hype example that I gave, the way decimals is 8 because the HyperCore amount is 1E8 for one hype. But each token has a different way decimals, which is a different decimals amount for HyperCore amounts. And then there's a EVM extra way decimals. So for hype, there would be 10 extra decimals on the EVM because it's 1E18 versus being 1E8 on HyperCore. So let's see what it is for USDTO. So this number is the way decimals. So 8, which means on HyperCore, if we wanted to represent one USD, like one USDT, it would be 1E8. So 1 times 10 to the 8. And then we see the EVM extra decimals is -2, which makes sense because the decimals of USDT on the EVM is 6. So it's 2 less than what's on HyperCore. So yeah, let me know if that makes sense. How to figure out how many decimals to use to represent a token amount.
Yeah,
Versus
actually, yeah. This is actually very confusing. I think even for people who are building an EVM, moving forward to like this, it's a little hard to, I think, understand. But also
right.
to answer the previous question when you said how will you like to find the identifier to call the hypercore to get uh, the value or to get the information from hypercore. So you got the address of the token, then you go to the registry that you just showed on HyperEVM, and
Yes.
and that's how you get the identifier, right?
Yeah, that's right. So
Oh.
there's no native way. So we built this simple contract, which so it reads from so there's a way to get the address of the token based on its index, For example, here, I put its index in, and we got the address out, but there's no way to do it in the reverse. But most developers are going to be working with addresses rather than indexes. So we made a contract which basically calls the same precompile with every index, and then it notes down a mapping from the address to the index. So now developers don't need to store the indexes at all. They can just work with the address and then use this contract, which we can link this. This is just a docs for the HyperEVM lib, which has many different features we'll talk about later. But one of them is just this public registry contract, which lets you get the token IDs from their address, which is pretty useful. So devs don't have to store the token IDs in their contracts because every token has a different ID integer.
Yeah, makes sense. And then there was also like 3 types of decimals that you just showed. Can you again just discuss what are those 3 decimals? What are the differences between all those 3?
Yep. Okay. So is there any way I can like type or write here or something, or should I just explain it verbally?
I think just maybe type it, open a doc, or if you want to type it anywhere.
Okay. Yeah, 1 second.
If you want, you can just start a Google Doc.
Yeah, good idea.
Yeah.
Okay. So it's well, let's just go back here first. So we only have HyperCore and HyperEVM, and the issue is that on HyperCore, token amounts can be in different represented with different decimals than HyperEVM. So to find the decimals on HyperCore, it's just called way decimals. It's like it's the terminology Hyperliquid uses in their docs. You can find this on their docs as well. So it's just called way decimals. And to find it, like to find what the way decimals is, we just have to go to L1 read, which has all the precompiles for us, and then pass in the token index. And then we look at the second last number. So in this case, it's 8. So I'll just go back and show you the struct. So yeah, the second last number gives us the way decimals. So that's the decimals on HyperCore. So I'll just give you an example as well. For USDTO, the way decimals is 8. So 1 USDT is equal to 1 E8. So that's how you would, that's what your balance would look like if you had 1 USDTO. Or if you had one, let's just look at a second example. So unit Bitcoin. So let's just get the token address first, because that's easy to get. And so it has 8 decimals on the EVM. Now we go to the registry to find its token ID, which is what we use for precompiles. And so now that we have the token ID, we go back to the token info precompile here and pass in the token ID. And so it returns us all the information about unit Bitcoin. And so the way decimals of unit Bitcoin is 10. So that means 1 unit Bitcoin equals 1 E10, because way decimals is equal to 10. And then we just have HyperEVM decimals, which is just the same. It's always going to be returned by the decimals function on the token contract, just like in any other EVM token. So you can just see it on Etherscan, like here, or you can just query the decimals function, but we don't have to do that.
Yeah.
Yeah. So it's 6 here. So on HyperEVM, one USDTO would be represented as 1E6, and one UBTC would be 1E8.
Yep.
So
Okay. Yeah. That's super
yeah.
clear now.
Okay, nice.
There
yeah,
is a question in the comment. Should I ask now, or you want to wait?
sure. Yeah, feel free.
Yeah. The question is why you couldn't implement token registry function as a native function of contract for HyperCore.
You mean why haven't they implemented it? Like
Yeah,
as a
I think
yeah.
I
So
think that's what the question says.
I think it could be implemented as an additional precompile, where you can
Mm,
pass in a EVM token address and then get a token index out. That would be a pretty useful feature for developers
yeah.
because everyone's used to working with token addresses and not working with indexes as the primary identifier for an asset. But I think it's not a I would guess that it's just not a major priority for them. Like there's much bigger things being worked on. And it's a
Okay.
pretty simple fix with just deploying our own contract that anyone can use. So I don't think it's a major it was a major like pressing matter to be dealt with.
Okay. Yeah, makes sense. And there is one more comment. I don't know if that's a question. So hype on HyperEVM is a wrapped one. Like, is it like a wrapped hype, or it's native hype, or what?
Right. So Hype it's the native token of HyperEVM, so it's the gas token. So
Uh-huh.
you can think of it as just ETH. It works the exact same way as ETH does on ETH or any L2s.
Yep. Good. And one last is that can we use Rust in HyperEVM? I'm assuming Solidity Viper as well, but what about Rust? No, right?
Yeah, no. So it would be any EVM smart contract languages.
Yeah. Yeah. Okay. Yeah, I think that's all the questions. Let's move ahead.
Cool. Okay. So here's another nuance. So on HyperCore, not every address is like accounted for by default. I think I think the main reason is just to reduce like state bloat. Like they don't have to account for all these addresses in their node until an address is actually like using the chain. So the way this is done is anytime you bridge tokens into your address or you transfer tokens into a specific address on HyperCore, you have to pay a one USD fee, and the fee is paid from the sender. So basically, if you don't do this, then the account it's treated like it doesn't exist. So if you made a contract on the EVM and then you moved you bridged USD from the contract into HyperCore, the balance on HyperCore would still say 0, and the reason is that it hasn't been activated on HyperCore. So right now, the only real way to activate these things is to manually go on Hyperliquid, like on their front end, and then go use an address that already has funds, and then just transfer a tiny amount of funds, like less than a fraction of a cent, and then one USD will be deducted from the sender's balance, and then your contract will now be actually activated for usage on HyperCore because it was only created on the EVM and it never interacted with HyperCore. So once it's activated, then any balances will show up, and you'll actually be able to do CoreWriter actions. So there's also a precompile here. Oh, actually, oh yeah, so here. So core user exists. And this just tells you, it just returns a Boolean whether or not the account has been activated or not. So if you try to send tokens, like if your contract, let's say, tries to send tokens to another account on HyperCore, and that account is not activated on HyperCore, then your contract is going to be deducted. It's going to have 1 USDC deducted from it, if that makes sense. So it's useful to use this precompile whenever your contract sends tokens on HyperCore to know whether or not that account is activated. So this is another weird or interesting feature of HyperEVM that developers would have to take into account.
So even though you use this precompiled, the users need to manually go to HyperCore to like activate it, right?
So it's yeah, the precompile is only for reading information.
Yeah.
So it just tells you if an account is activated or not. So it's useful for smart contracts which are doing actions on HyperCore, and they want to know because if they're going to send tokens to an address, if that's encoded in the contract logic, it's important to know if that address is activated or not. Because if it's not, then the contract is going to have 1 USDC deducted from it. So it's more of a security consideration I was going to speak of as well
I
on the
see.
smart contract.
But once the 1 USDC is deducted, the account will be activated or still not activated.
Yes, so once it's deducted, then the account that we sent tokens to will be activated. So now that account can interact with HyperCore, and its balances will be visible.
And also, I saw someone asking a question in the Hyperliquid Discord that you need some amount of token on HyperCore to like deploy contracts on HyperEVM. Is that true?
To deploy contracts on HyperEVM,
Yeah. Do you need some balance on HyperCore?
I don't think that's the case. I think to deploy on EVM, you don't. You just need to make sure you have hype on the EVM to pay gas. But there are similar situations where, well, if you want to bridge any token from HyperCore onto HyperEVM, you do have to hold some hype on HyperCore, weirdly enough, even though it's not being bridged. Like if you want to bridge unit Bitcoin from HyperCore to the EVM, you will have to hold a small amount of hype. Otherwise, the bridging action will just fail.
Wow. And there is no fees to bridge, right?
Well, yeah. So I can actually go over how the bridging works. That would be useful. Okay, just a second. So I'll just open the repo for the library, which shows how this works. Yeah, so if we want to bridge tokens from HyperEVM to HyperCore, or if we want to bridge Hype itself, all we have to do is we have to send tokens to a specific system address. So let's just see how the system address is calculated. So it just comes from adding the tokens index, which is that number we spoke about before that you can derive based on its address, and then you add it to the base system address, and then you just send the tokens to that address on the EVM. And then once you do that, it'll be credited to your to the same address which you sent it from on HyperCore. So that's how the bridging works from HyperEVM to HyperCore. And so the fees here would just be, the gas that you pay on the EVM to perform the token transfer. And then if you want to bridge from core back to the EVM, this is how it would work under the hood. So we can ignore all this, which is just converting the token amounts due to the decimals issue that we spoke about before. But all we have to do is call this spot send function, which actually just calls an action on the CoreWriter, which is what we use to perform actions from the EVM on HyperCore. So since we have balances on HyperCore that we want to move to the EVM, we need to use the CoreWriter to do that. So to bridge from core to the EVM, we call this spot send action on the CoreWriter, and we set the recipient as that same system address. So we're effectively sending tokens to that system address, but on a HyperCore, and then they'll end up on the EVM. They'll end up back in this contract on HyperEVM. So there's quite a lot of logic here that would be tedious for developers to write, which is why this is a library which anyone can import, and they can simply just call these functions. So it'll just look like this, like in your actual contract, where you just call CoreWriter lib .bridge to core, and then all of that, the decimals handling can happen under the hood. Okay.
Interesting. Okay. This is way too complex.
Okay, I'll do my best to explain anything if it's unclear.
Yeah. No, I think it's pretty clear, but I think it's, as a developer, it's just a lot of things, a lot of nuances to handle, right?
Yeah, that's right. We try to make it as simple as possible with the lib.
Yep. And also, I don't know if you are going to cover this, but a lot of people don't know that in Hyperliquid there are like two types of block. One is smaller block and one is the bigger block. I think the smaller block is every second and bigger block is every 3 seconds or something, right? And then whenever you're trying to deploy the contracts, you deploy it on the bigger block mostly.
Yeah, that's a good thing to bring up. So there's two types of blocks. The main difference between them, like from the developer's POV, is that they have very different gas limits. So small blocks, I think it's either 2 million or 3 million, but the big blocks have a 30 million gas limit, which is more like I think that's the same as what ETH mainnet has. So for large transactions like contract creation, they're often going to fail. Like they're going to use up more than 2 or 3 million gas, which means you're going to have to use the big blocks to perform deployments. They might take more time to finalize, but I can go to this website which shows you. Makes it easy to toggle. I can't seem to find it.
Oh, there is a website. Nice.
Yeah, because it's a bit tedious to do it without the front end. Okay, I can't seem to find it. I had it saved somewhere. Just give me a second. Oh yeah. Okay. So you can use this. I don't have my wallet on this browser profile, but it just lets you connect your wallet and then change your config, because it's not. It's a bit like the way you do it is by calling actions on HyperCore through your EOA. So it's not straightforward to do like via via your like IDE, you'd have to like tap into the SDK to change this, or you can just use this front end and connect your wallet, your dev wallet, and then change between big and small before you deploy a contract.
Wow, crazy. Okay, and because
Yeah.
this is on HyperCore, so you have to actually call the precompile, right?
So not a precompile, but the typical way, whenever you use Hyperliquid, like from their front
Mm-hmm.
end, is
Mm-hmm.
you sign an action, and then it gets sent to their API, and then um, it gets like included. So whenever you're interacting with HyperCore, you're not paying any gas. You're just performing these actions by signing something and then sending it to their API. So since this is a HyperCore action, that's what would happen under the hood. It would sign something and then send it to their API, which is a bit no, like you can't do this in Foundry. Like have a uh, you'd have to be calling their API or using the SDK to do this,
Okay, and
which is
also
why
I'm curious.
yep.
Sorry, I'm curious about create and create to. Is that available on HyperEVM?
Yes, you can use both
Okay,
create and create to for deploying.
I see.
And
Okay.
also the typical create two factories are deployed, like which we find on any chain, are also deployed on HyperEVM at the same address. So you can, if you used a create two factory to deploy a contract on like any other chain like mainnet, you can deploy your contracts on the same address on HyperEVM by just using the same salt and the same factory address.
Okay, nice. Okay, yeah, I don't see any question in the comments, so we can move forward.
Okay, cool. So yeah, so this was just about the account activation. One more thing that's useful to talk about is the different block explorers. So on HyperEVM, uh, we have HyperEVM scan, which is the one I was on before. This one that looks just like Etherscan because it's by Etherscan. This didn't exist for a while. So there used to be devs used to rely on different ones, and the different ones are still actually useful even though we now have HyperEVM scan. So I'll just explain why here. So there's this one called Persec, which is from the team at Parsec. And the useful thing about this one, while it looks different to like Etherscan, and it's a bit tedious to use like for looking at your transactions or like looking at your contracts. The benefit is that it lets you track portfolios very well. So let me just quickly find an address that that actually has assets. Okay, 1 second. Okay, this is a bit hard. Um, okay, we'll try this one. Okay, it would have been better to have a example.
Mm-hmm.
Okay, great. So here we have a account, and we can see its balances on HyperCore. And so on HyperCore, it has this amount of USDC in its spot balance. And on HyperCore, you can also have a perp balance, which is just like the tokens being used for perp trading. And if this account did have a perp balance, it would be shown separately here. And then if they had a staking balance of Hype, it would also be shown separately. And then we can also see their EVM token balances. And you can also see like all this different data. So this is not available on HyperEVM Scan because HyperEVM Scan is only for the EVM. So you don't get to see anything about HyperCore balances. So if you're building something that's integrating with HyperCore, for example, just anything that's any contract that also trades, like makes perp trades on HyperCore, then you'd want to use PerSec in your testing and also like after deployment, because then you get to see the different balances on HyperCore and not just EVM, which is what you get with HyperEVM Scan. So yeah, this is the main benefit that I see and have used with PerSec, where you get to see HyperCore balances and they're all differentiated very well. So then we have HyperEVM Scan, which is, there's not much to say. It's just the same as Etherscan. It's very good for looking at your transactions you're doing, like what is the call data, and then also just looking through contracts or even interacting with them through this interface. And then the last one is the official Hyperliquid Explorer. And this lets you, it's insanely quick, and it lets you see any actions you've done on HyperCore. So here's one. It's a trade where someone's shorting this token. And so whenever you perform actions from the EVM, which use the CoreWriter to do things like trade on HyperCore or send tokens to someone on HyperCore, it will show up on this Explorer as a transaction. And so you can go to your contract, if we imagine this is a contract, and then you can see all the different CoreWriter actions that happened. And sometimes if an action fails, then there would be another field here called error. And so that's how you would debug your transactions. Because if you're on HyperEVM Scan, you don't see the HyperCore transactions, you only see the EVM ones. And it's the same with PerSec, where it only gives you EVM transactions. It doesn't give you HyperCore ones. So anytime you need to debug your HyperCore transactions, like this one is to cancel an order, then you'd use the official Hyperliquid Explorer. So yeah, those are the three main ones that you'd be using as a developer.
Oh, nice. And also, if anyone is watching, I mean, we will share this slides later on in the comments, so you can check it out. Right, Johan? We can share it, right?
Yeah, sure.
Okay. Awesome. Yeah, let's move forward.
Okay. So next, we'll move on to some security considerations. So the first one is, it's just that whenever you perform a CoreWriter action, this is the contract. So all it does is emit an event. Well, it wastes some gas first to prevent spamming, and then it emits an event, which is read by the nodes to actually like queue the action on HyperCore. And this means that if the action fails on HyperCore, it wouldn't revert on the EVM. So it would just seem like it succeeded because nothing happened. The transaction just completed, but the actions can still fail on HyperCore. So if you looked at your contract and then went to the action, it would say, like, if the action failed. Yes, so this is an example of a failed action where it says error and then you have an error message. So if you tried to, for example, trade like more than your actual balance, if you tried to sell more of a token than you had, it would succeed. It would seem to succeed on the EVM, but you shouldn't assume that it actually succeeded, and you can't really know in the same, like within the transaction, if it succeeded or not. So you would have to, you'd only be able to know once the transaction is actually sent to HyperCore. So that's one thing to keep in mind. And another one is that precompile calls only return data from the start of the EVM block. So if we imagine a contract where it starts with 0 USDC on HyperCore, and then it sends a CoreWriter action, which is to, which is to sell one BTC for 100K. And then it reads the USDC balance from the precompile. So let's just go and see which precompile would do this for reference. It would be the spot balance precompile. So we'd pass in a user's address, and then we'd pass in that token index, and then it would return the balance of the user. Like it does a few different values, and then yeah, so the balance returned would still be 0, even though the contract had sold one BTC for 100K USDC. And that's because the precompile call that you made in step 3, it doesn't register the CoreWriter action which you sent in step 2, because you should think of these CoreWriter actions as just queuing an action. So it's just sending it, it's an empty function which is just sending an action to be queued to happen later, but it doesn't actually happen instantly, which means in step 2, when we do the CoreWriter action to sell one BTC for 100K USDC, it hasn't actually happened on HyperCore, which means in the same transaction, when we read the USDC balance from the precompile, it's going to return this starting USDC balance, ignoring this trade here, because it hasn't happened yet. It only is reflected in the next block. And yes, this can lead to a lot of different issues if it's not accounted for, because if the developer expects the balance to be 100K, but it's actually 0, then one example of an issue would be instead of reading USDC's balance, if we assume it was reading the Bitcoin balance, then the developer would expect the Bitcoin balance to be 0 after selling it for 100K USDC. If we assume the initial balance was 1, and then when we read the Bitcoin balance from the precompile in the third step, since the action hadn't actually happened yet, the balance would return 1. It's I don't have it on the slide, so it might be a bit confusing. But effectively, when the balance returned is always going to be the balance from the start. But if you don't account for this when writing your contracts, there could be critical exploits due to like, expecting the wrong values. Tom, if we have time, I can show an example of this.
Sure, yeah.
Okay, just give me a second.
Yeah, since you're looking to that, in the meanwhile, if anybody of you is like building, you can go to alchemy.com/hyperEVM. We have support for the APIs and RPCs and also smart wallets. So just if you use the RPC API, you can also call the HyperCore, as just Johan mentioned right now. You can just do the CoreWriter call and also query HyperCore. So go to alchemy.com/hyperliquid and get your API keys. Over to you, Jan.
Okay, just a second. Okay, so we have this example contract, which was put together with an intentional critical issue. So I'll just first quickly explain how it works. So basically USDC doesn't exist as a contract on HyperEVM yet, but it does exist on HyperCore. So this aims to be a wrapper of HyperCore's USDC on HyperEVM. So a way to tokenize the USDC on HyperCore and use it on the EVM. So it should be backed one-to-one. And there's this contract can be ignored. And then this contract is just the actual token. It can also be ignored. And then here's just this issuer. And it has two key functions. One called initiate mint request, and then one called complete mint. And it's quite a lot to digest, to explain quickly. But the idea is we can see there's many precompiles being called. So get spot balance is calling the spot balance precompile, which is here. So it's calling the spot balance precompile, and then it's requiring that it's greater than. It's requiring that a snapshot, which is something from before, is greater than the actual spot balance. And the key thing is that, oh wait, actually, Uttam, I think this is going to take quite a while to explain, like the actual vulnerability.
It's
Is it
fine.
fine if
We
I
can
do it?
skip it. I mean, up to
Oh,
you. I mean, if you have time, then for sure, let's go. But I also know that you might have to go. So totally up to you. Your call.
yeah. You know what? For now, I'll just I'll explain the root cause, and then I can link an article for people to read if they're interested on the actual
Yeah.
the whole impact of the issue and everything. But the root cause is just this concept that if I go back here, that precompile reads will always return information from the start of the EVM block, regardless of any CoreWriter actions which we placed, because you should always think of them as sending an action which only is reflected in the next EVM block. So we wouldn't see it when we perform read actions in the same block.
Okay. Yep, that makes sense. I will link the article in the comments and to the live stream on YouTube. So if anybody's watching later, you can check out the article if you want to learn more.
Okay, cool. So the final thing is just I'll quickly overview the HyperEVM lib and how it can be useful for developers. So we've already touched on it a bit, but it's just an all-in-one library for building and for testing smart contracts on HyperEVM. So for building contracts, we have two key aspects. I'll go to the docs here. There's one called the CoreWriter lib, which just trivializes all the different intricacies and footguns that you might come across when trying to perform actions with the CoreWriter. And then for using it all you'd have to do is import this lib, and then here's an example for bridging, where, well, bridging doesn't actually use the CoreWriter when bridging to HyperCore, but when bridging to the EVM, it does use the CoreWriter, and it's a lot easier to just use this library rather than implementing the like having every single contract developer implement the underlying logic on their own. So yeah, here's just one example. And then for the read precompiles, we just provide a simple like interface for finding the spot price or anything you might want to read by just passing in the token address instead of passing in the index, because that's an unusual thing to be like referencing a token with. So you can just pass in the token address, and then under the hood, it would convert the address into the necessary identifier, and then call the precompiles. And then the second aspect of the HyperEVM lib is the testing aspect. So when testing a contract on the HyperEVM, if you want to test run local tests, you'd most likely run into this error where when you try to call a precompile, it doesn't exist in Foundry's local simulation, which means the call is going to fail. So you can't really test any contracts if they use precompiles, which is a big limitation. And the reason is just that Foundry runs a default EVM, which doesn't have HyperEVM's unique features like the precompiles. So it just thinks you're calling an address which has no code on it. So the solution that we provide is we made this this library called the Core Simulator lib. So all you have to do is import this into your test and then initialize it within the setup of your test. And now you can make any precompile calls, and instead of failing like they do here, they would just succeed, and it returns information live from from mainnet or testnet, whichever one you're using, and it just gets it from the RPC. So the precompile calls will now work, and then let's say you perform a CoreWriter action. For example, you well, let's say you bridge to core. Then we have contracts under the hood, which are initialized here, which will account for that. And they basically store all of HyperCore's state, which is not in Foundry by default. And so then you can go to the next block, because any actions will only be reflected in the next block. And then we don't have it here in this example, but you could then read from a precompile, and it would actually reflect this action. It would reflect the balance update from this bridging action, which means just by like adding this import, you can now test any interactions between HyperEVM and HyperCore, which was previously not possible in Foundry. So now you can run fork tests for your entire project, which interacts with precompiles and CoreWriter, and they'll be pretty accurate. Like they'll be 95% accurate to actually running the tests on mainnet. So previously, before this, every developer would just have to test in production. They would have to be running Foundry scripts, which is annoying because you can't reverse them, and you have to like load up your wallet and pay gas every time. But now you can do a lot of your testing locally, and it's much quicker. And you can keep iterating and changing things using this this local simulation library. And I think that's it from me for the for explaining how the lib works. You can go to this website hyperlib.dev to uh,
Yeah, I
find out
shared
all
that
the.
in the comments.
Okay, nice. Yeah. So this docs page has all the information on how to get started, how to install it in your library, just running this command, how to install it into your contracts. So yeah.
Awesome. Yeah, I think that wraps our session for today. I mean, do you have 2 more minutes for a question that I see in the comments, or?
Yeah, yeah, I do.
Yeah, so there was one more question is does the precompile function return the actual balance after the queued action got processed by the main EVM, or it never shows actual balance? You can also see the question on screen.
Uh, Sorry for the infinite loop. Uh, does the precompile function return the actual balance? So is this regarding the testing framework, or like in reality?
I think it's related to testing.
So with the testing, once we once we test the bridging through this by calling the bridge function on our example contract, and then we simulate moving to the next block in our test, then if we added a function here if we added a call here read to read the balance of this contract, it would indeed increase, and that's the same as what would happen in like on the EVM if we did this. If we did this as a script, it would the balance would be reflected after the next block, and precompiles would show us that.
Okay, okay. Just one last question, which is how can usually developer handle the error in HyperEVM? Is there any way to get transaction hash in HyperCore? You said HyperCore throw error, but HyperEVM cannot catch the error.
Yeah. So yeah. So HyperEVM on HyperEVM, when you send actions to HyperCore, they just get sent to this contract, which will never revert because it hasn't actually even performed the action yet. So it doesn't know if it's going to succeed or not. The action just gets queued on HyperCore, and it will be reflected in the next EVM block. So if we want to know if the action succeeded or not, then you would go to your contract on the Explorer. So let's say that this is our contract, this address. You'd go to it on the official Hyperliquid Explorer, and then you can see all the actions that have happened before. And then you would just click into whichever one you did, like based on the time. And then if it has this error field here, then that means the transaction failed. And then thankfully they give you the reason as well. They tell you why it failed. And that should be enough information for you to figure out why why the CoreWriter action failed. So you wouldn't be notified on the EVM. It wouldn't revert your transaction, but this is how you would check if your transaction succeeded or not.
Awesome. Yeah, I think that's it. We are out of the time. Bjorn, can you hear me?
Yep.
Okay, yeah. So, all right, that's it. I think that's enough for today and for this session. So, we are gonna wrap up. And thank you also everyone who joined in, asked question, and kept the energy high. And if you got liquidated today, at least now you have leveled up on like chain knowledge, and so get and start building on Hyperliquid. I think the ecosystem is just getting started. You still have a lot of time. You can still be early. Um, just start building on HyperEVM. And thank you so much again, John. I mean, this was an astonishing session. I really learned a lot. And I'm pretty sure a lot of people have learned a lot because Hyperliquid is such a complex ecosystem that so many of developers who even wants to build, they are confused of what HyperEVM is, how do we start building, and all these security considerations. So this was really helpful, and I would really advise everyone to go to hyperlib.dev as well, and check out their documentation and all this awesome library. And thank you all for this. Thank you, John, for all this community work of building this amazing library.
Yeah, no worries. Glad to hear that you found this useful. If anyone has any questions or if anything was unclear, feel free to DM me on Twitter or Telegram, and I'll be happy to help you out with whatever you're building.
Oh, that's awesome. Yeah, feel free to give him a follow on Twitter again. And there are actually almost 600 people watching us live on all,
Wow.
including all the social media platforms. So this was really awesome. Cool. Thank you so much. Take care, and good morning, good night, good evening, wherever you are. Thanks for joining in. Peace.